Hello everyone, my name is Mahreen Chowdhury. Today we will be discussing Lab 3 circuits. The purpose of this lab is to use the principles of energy conservation and current conservation to predict the behaviors of circuits containing resistors in series and parallel, use multimeters to measure the values of conventional current potential differences in the circuits, and examine the behavior of resistors and capacitors. We use ammeters, voltmeters, LEDs, wires, batteries, light bulbs, an online circuit construction kit, and Google Sheets to do this experiment. The results we found were that the resistances of the R47 resistor is 48 ohms, the R100 resistor is 102 ohms, and the wire and the ammeter are 0 ohms. Charging and discharging of the capacitor is approximately equal of 10 seconds. The first fundamental physics principle I'll be using in this lab is the node rule, and this states that the current flowing into a node must be equal to the current flowing out of it. This is a result of the conservation of charge. Next is the loop rule, which states that the sum of all of the electric potential differences around the loop is zero, and this is a result of the conservation of energy. Lastly, we got Ohm's law, which states that the current conductor between 2 points is directly proportional to the voltage, and it is formulated by V equals IR. Let's start by exploring charge and energy conservation in series circuits. We're given this diagram and told to predict the currents that would be measured by two different ammeters. We have the initial conditions of 3V and 147 ohms, which is the total resistance. We have to consider that the current is the same everywhere in the circuit by the loop rule. By using Ohm's law, we find that the current is 0.0204 amperes, and this also matches our online simulation. We can prove this calculation by stimulating the exact circuit online, placing an ammeter. We can see that the current matches what we calculated, and when we reverse one of the connections to one of the ammeters, nothing changes. When we replace one of the ammeters with a voltmeter, two things happen. The ammeter is going to read 0 amps because the voltmeter has extremely high resistance, basically making this circuit an open circuit. And the voltmeter is going to read -3 volts, since there is no other voltage drop in the circuit. Now we can find the voltage drop across each different part of the circuit, but the only places we're going to see a voltage drop is if there is some type of load, like a resistor or a battery. We can use the loop rule and Ohm's law to find those values and calculate. As you can see here, we find that the net value is 0. We're going to replace the voltmeter with an ammeter in parallel with the 100 ohm resistor. Ammeters have very low resistance, so current will go through it instead of the 100 ohm. So this is going to lower the resistance to 47 ohms, which offers near zero resistance compared to the 100 ohm resistor. We're going to find that the current is going to be 0.06, and stimulating this online, we find the same results. The graph visualizes the voltage gain and drop as we go around the circuit. The batteries contribute voltage gain and the resistors contribute to voltage drop. Voltage with higher resistance is showing a more significant drop, and we can see the sum of all the voltages leading up to 0. When we attach a voltmeter to the circuit, the ammeter reading doesn't change. This is because the voltmeter has extremely high resistance, so almost no current flows through it, and this has no effect on the path and speed of the electrons. Going on to resistor circuits, the initial conditions were 1.5 voltage batteries, and we had two of them, 1 farad capacitor and a 10 and 20 ohm light bulb. We created a circuit for the 10 ohm resistor and another circuit for the 20 ohm resistor, and that involves a capacitor, and then it measured the time it took to charge the capacitor and discharge. For the 10 ohm circuit, it took about 10 seconds, and for the 20 ohm circuit, it took about 20 seconds. Next, I graphed the experimental relationship between the natural log of the current voltage over initial voltage versus time. In order to find the time constant, which is ideally found by multiplying the resistor and capacitor values, we see a linear and decreasing relationship between the two, and the experimental value of 11.4 seconds is pretty close to the predicted value of 10 seconds. Here are some images of our RC circuit from lab. In this lab, there are some sources of error, including human error in properly positioning the circuit to take measurements. The model is not accurate of real-world scenarios, and human error in recording the time and then stopping the capacitor from discharging, both at the same time. For our further discussion into the results, what would happen if we charged a capacitor with no resistor in the circuit? An ideal model would charge the capacitor instantaneously with no resistance. However, in real life, this would not happen because there is no such thing as zero resistance. In fact, actual batteries have internal resistance. The measured time of 10 seconds for the capacitor to charge is due to the internal resistance of the battery, wire resistance, and the capacitor's characteristics, all of which slow down the charging process. In contrast, the ideal model assumes no resistance, predicting an instantaneous charge, which is not realistic in practical circuits.